possible to compute the solutions also when delta is negative, but we have to extend our set to the set of complex numbers, okay? We are not, for the moment, we're not interested in it. Here are some qualitative examples, but basically, what is parameter A? Parameter A controls whether it is convex or concave. If A is positive, then B basically controls whether the symmetry axis, which is this vertical line. Okay, so I should, yeah, but if I turn them off, then participants. If I mute them all, okay, the participants, and then I can see. Okay. Please, Wakar, can you please turn your microphone off? I can do it. Okay, but then he cannot make many intervention or.
Yeah, he can turn on again.
Oh, he can turn it out again. So what is my role as a leader? Very strong leader. Okay. Okay. So if A is positive, for instance, and B is negative, like in this case, then the symmetry axis is on the half plane of positive x. Okay. Vice versa if B is positive. So B basically B jointly with A controls whether the symmetry axis is a vertical line lying on the half plane of positive x or of negative x. Okay. What about C? If you look at the equation, C, you obtain here C if you set x equal to 0. So if you set x equal to 0, y is equal to C. So C represents the point of intersection. It is the intercept, basically. It's the point of intersection with the vertical axis, okay? So based on these elementary considerations, you can represent different cases for the parabola here, okay? I try to summarize, not all of them, but many of them, just to understand the basic mechanisms. If the discriminant, this quantity, is positive or 0, then you can compute analytically, you will know the two solutions, the 2 points of intersections with the x-axis. And this is the formula, very common and popular formula. Okay, just look at this. Graph here. Of course, this is what I mentioned earlier, Desmos. It's very friendly, you can learn it immediately. It is possible to write the equation. I can show you how to do that, just to let you know. I remove all of this stuff. I start again from the beginning. Of course, I can write a function. Just don't need to write y equal to. Just write 3x plus 2. And this is a straight line, okay? If I want to write a quadratic function and I want to add exponents, it's very easy to add the exponents. 3x squared is a parabola, for instance. But I can also write functions that depend on a parameter ax squared plus bx plus c, ax squared. Now, the system understands that there is a parameter here. So do you want to add a slider? Slider means that I can change the value of this parameter very quickly. So I add the slider. And the basic value is a equal to 1 plus bx plus c. So I must add 2 more sliders. Okay? And now what is the standard values for all these parameters is 1. So this means that now I'm representing the function y equal to x2 plus x plus 1, which is precisely this one. Let me see if everything corresponds to what we learned earlier. The point C is the intercept, is equal to 1. Okay? A is positive and it controls the concavity, so it is upward concave. What about B? Remember that the abscissa of the vertex is minus B over 2A. Sorry, 2A. Okay? Minus B over 2A is the abscissa of the vertex. The abscissa here is minus 0.5. You can see the value. Okay? What about the discriminant of this parabola? Discriminant, we don't see any intersection with the x-axis. The discriminant will be negative in this case, okay? So it is b squared minus 4 ac, you're just right. And you see that the discriminant is actually negative, okay? So here, there is no x here, so no functions is represented here. You just add parameters, you assign values to these parameters, and you can see immediately the numerical result. What about the abscissa, the equation of the symmetry axis? The symmetry axis is a vertical line. So it has an equation of the type x equal to something, okay? So if I write here x equal to minus b over 2a, which is the same abscissa of the vertex, because the vertex belongs to the symmetry axis, of course. So minus b over 2a, I see this vertical straight line, which is the symmetry axis for the parabola. Then there is a way to change, I mean, whether you want thick lines or thin lines, the colors, various types of lines, and there is everything inside, okay? But this is just a way to see, you see it's very useful to check the results of your exercises, to see what happens if something changes, etc. Okay? So basically, if I change now parameter C, and you can move the slider here or just change the value here. C equal, for instance, to minus 2, what happens? Now the parabola has the vertex on the negative part, okay? So it crosses the x-axis in 2 points, okay? So these are the 2 points. You can numerically see the solutions by clicking on the points, of course. So this is a situation in which we have the crossing of the x-axis. We can, for instance, change our A and make it become a concave parabola. For instance, if A is equal to minus 1, then we have something like this, okay? And we can, for instance, now put back C equal to 1. And we have a concave parabola that again crosses the axis in 2 points. So you can check, when you study something in theory, you can see immediately in practice how functions look like, which is very useful. There is also a way to study not just, I mean, maybe also 2 variable functions, but for sure implicit forms, so written as 2 variable functions of 1 variable function. So you can also get a representation of a function written in implicit form, or properties that you can compute in integrals and whatever, okay? So I think that graphically it's not possible to see 2 variable functions, but all other kinds of computations and visualizations are possible, okay? So if you, I mean, I don't spend more time on the parabola, except letting you solve a simple exercise to show one thing, and then we will switch to power functions. Given the quadratic function 2 plus 1/2 x minus 1 over 20 x squared, find the maximum point of this function as well as its maximum value. Find the points of intersection with the x-axis, that is the solutions to the equation f of x equal to 0. And provide a graphical representation of this quadratic function along with the graph of this very similar linear function. It is 2 plus 1/2 x, so there is a quadratic term missing here, but for the rest it is, the remaining part is the same, okay? Okay, the maximum, in general, we find maximum points using derivatives, but in this particular case we know that it is the abscissa of the vertex provided that the parabola is concave. The parabola is concave because A is negative. So this is a concave parabola. These are the values of the parameters. This is the abscissa of the vertex, minus b over 2a. You can compute it. It is 5. Of course, it is the maximum point of this function. What is the maximum value? Now we distinguish, this is a general concept, between the maximum point and the maximum value. The maximum point is the abscissa. Look at the picture here. The maximum point is the abscissa, is the value of x where the function reaches its maximum. The maximum value is the corresponding value on the vertical axis. Okay? It's the value taken by the function at x star. Okay? So the maximum value can be computed by replacing x star equal to 5 into the equation of the parabola, and we get 13 over 4. By the way, there is also a general formula for this because this is the vertical coordinate of the vertex, and we know that there is an expression in terms of A, B, and C. Okay? So you can also do that by just using the expression for the vertical coordinate of the vertex. Okay? The discriminant is delta, capital delta equal to 13 over 20. It is strictly positive. We will have two different intersections with the x-axis. We can compute the intersections by applying the formula. So this exercise is just a summary of what we need about the parabola. Okay? You can compute this by this formula. You obtain two values, usually written in this way, the plus minus here. So it's 5 times 1 plus minus square root of 13 over 5. These are the two values. This is the maximum point. Of course, the two values are symmetric with respect to the symmetry axis here. Okay? And I mean, anything else should be clear here. This is the representation of the results of our exercise. And this is the representation of the straight line of equation 2 plus 1/2 x. The exercise per se is very easy, but I use this to emphasize one thing. It turns out by using the calculus later that this is exactly the best linear approximation to the parabola at the point of abscissa 0. Okay? It is the tangent line to the parabola at the point of abscissa 0. If you look at the expression of the parabola and the straight line, clearly when x is very close to 0, the quadratic term, in this case, it has a very small coefficient, okay? But even if this coefficient is 1, for instance, minus 1, the quadratic term doesn't matter. It doesn't matter because, for instance, 0.1 squared is 0.01, okay? So it changes very little with respect to the other part, okay? And you can see it very clearly from the graph. If you remain near point 2, you can some sense replace your parabola with a straight line to study the behavior of this quantity when x changes close near 0. Of course, the larger becomes x on the left or on the right of 0, the more this term matters, up to the point where basically the qualitative behavior changes strongly. Okay? Now if you increase x, the parabola decreases. This is just to show you what is the meaning of approximating linearly near a point. Clearly, there is a very little difference near the point 0 and a large difference far from 0 in this case. Okay, so this is basically what we need about the parabola. Let me now go to the power functions. They are already, I have uploaded already to the Virtuale yesterday. They belong to tomorrow's class, but of course we can start it today. power functions. So in principle, this is not so easy. I mean, as the straight line or the parabola. There are some delicate points about power functions. What is the general form of a power function to us is of this type. Capital A is any constant. It can be positive or negative, times x to the power of r. X must be strictly positive. Next I will explain why. Of course, if r is 2, r can be any constant, any real number. Clearly, if r is 2, it is x squared. And in principle, x could also be negative. But if r, for instance, is -1, then it is a divided by x. Okay? So in this case, x, for instance, cannot be 0. If r is equal to 0.5, I have here a times the square root of x. And in this case, x must be non-negative. If you want to have a general expression for this function that includes all the cases, you must impose that x is strictly positive. Because if x is strictly positive, this is well defined for any constant r, for any real exponent r. Okay? This is why we usually set x strictly positive. In some cases, of course, x can also be negative or 0. In particular, if this exponent, which is a real number, any real number, is the ratio between two integers, positive or negative, and n in the denominator is different from 0, then we have an exponent which is basically expressed as a fraction. And we can write our power function, assuming a equal to 1 for simplicity, here the constant capital A equal to 1. X to the power of r is x to the power of m over n, so it is the nth root of x to the power of m. Okay? For instance, x to the power of -3 over 5, negative exponent means 1 over the same power function with the positive exponent. 1 over x to the power of 3 over 5, so 1 over the fifth root of x to the power of 3, basically. Okay? Clear? The graph. The graph changes a lot depending on, okay, we now assume that A is positive. Just one thing. We now assume that A is positive. In general, if I have this function, and my function is like this. If I consider the other function minus f of x, its graph is this one. So it is symmetric with respect to the x-axis, okay? For the power function, I take a positive for the examples. If a is negative, it is exactly the symmetric with respect to the x-axis, okay? This is the reason why I only consider a positive. Okay? And also, I consider a, okay? And also, I consider a equal to 1 for simplicity. If a is equal to 2, the behavior is qualitatively the same, but there is a factor of 2, so it increases more just from the beginning. Okay, I will show you with the Desmos some examples of what is the impact of capital A. Okay, so it's very convenient to consider the basic case x to the power of r with a equal to 1, okay? Because qualitatively nothing changes if then a is 2 qualitatively. Okay, this is the case in which we have the exponent between 0 and 1. This is one of the most important in economics because it includes the assumption of a function which is defined for positive values of the variable. It is increasing and it is concave. So basically, it includes, it embodies the idea, for instance, of decreasing marginal values of the function, okay? So it increases, but the slope is, it is less and less sloped, basically. Anyway, the slope is always positive. And this is the typical case of a power function with the exponent between 0 and 1. The basic case is the square root of x, but also x to the power of 1/3, 1/4, 2/3, and whatever, okay? All cases are similar qualitatively to this one. This is the case in which r is positive and larger than 1, which is a branch of a parabola, basically. In the case, for instance, r equal to 2, this is just the right branch of a parabola. What happens qualitatively, there is a big difference because this is increasing and convex. So we have increasing marginal values. Marginal values are basically the slope, okay? And the slope is increasing. Here the slope is positive but decreasing. Here the slope is positive but increasing. Then there is the case, of course there is a particular case when r is equal to 1. If r is equal to 1, this is a linear function, okay? It's x to the power of 1. It is x, it's just the purple graph here. It's the bisector of the first quadrant, okay? Y equal to x, f of x equal to x. This is a case where r is negative. For instance, 1 over x squared, which is as a behavior like this. So what is the behavior in this? You know, x must be positive, but if it gets closer and closer to 0, then this explodes, becomes very large, okay? So when x goes this direction and approaches 0, then the function becomes higher and higher. When x becomes higher and higher, we say it tends to plus infinity, then the function becomes closer and closer to 0. And this is the typical. It is a kind of branch of, similar to the branch of a hyperbola, for those who know something about analytic geometry. And this is the case of r equal to 0, the orange one, in which the function is x to the power of 0, so it is a constant equal to 1, okay? Well, these are the possible examples of a power function. All power functions, independent of the exponents, pass through the point 1, 1, okay? So just to go back. Here is an example. This could be, qualitatively I mean, this is the 0.11, and this could be x to the power of 3 over 2. Okay? And this one could be x to the power of 1/3, I mean qualitatively, passing through the same 0.11, and this is could be 1 over square root of x. Okay? All these functions pass through the 0.11. But they are very different, of course. Okay? Let me say something about the exponential function. Let me start this part. Exponential functions are the most important, one of the most important classes of functions in economic applications and in applications to all applied sciences. I mean, biology, chemistry, economics, finance. Finance is built on the properties of exponential functions, basically. And geometric progressions, elementary mathematical finance is based on geometric progression, a large part of, and finance is based on exponential functions, in which, of course, then you may have a different type. You can extend to random environments, but basically we have exponential functions and logarithms, which is the mirror image of the exponential function. Okay, so first of all, the general form of an exponential function the general form of an exponential function is again like this, is a capital A constant, which for simplicity we take it positive, but if we take it negative, everything is mirrored by the horizontal axis, okay? So it's a mirror image. Times A is a positive parameter, which is called base of this power, to the power of x. So what is the main difference with the power function? Both are defined in terms of a power, but in the power function, the independent variable is the base of the power, and the parameter is the exponent, like this. The variable is the exponent, and the parameter is the base, which is assumed to be positive. Okay? So the main property of the power function, you remember in the linear function we studied what happens. It's very useful to contrast. To contrast it with the linear function. And for the linear we studied what happens in terms of the increasing independent variable by 1 unit. I want to increase the independent variable by 1 unit, okay? And I study of the dependent variable in terms of difference. So this is the absolute change in terms of a difference. With the exponent, Exponential function, we do the same, not in terms of difference, but in terms of the, this is called growth factor. It's not the difference between the value at t plus 1 and the value at t, or the value at x plus 1 and the value at x, but it is the ratio between the two values. This is called growth factor, okay? So if this is equal to 1.05, this means that there has been a 5% increase, okay? The next value, divided by the previous value, is 1.05. So the value of the dependent variable has increased by 5%, by 0.05, which is 5%, okay? So this is really important.